Okay. We're recording. All right. There's no internet today. You already know that because you can't zoom in. So what I'm trying to do is use different programs and record the activity here and the activity that's on the screen and splice them together later. If it doesn't work, you may get one or the other or neither. Just a word of warning. So let me start the screen recording and pull it up. Let's see. Where did it go? Here it is. Okay. And this should make it full screen. All right. If it works, good. If it doesn't, you'll be the only witness. So, for the last exam, and I do believe, right, we just have 4 exams, no final. So this exam will be during finals week. Chapter 9, we'll have Chapter 9 and 10 covered in this exam. So let me see, I'm going to have to, well, I could. No, I can't. I don't have a place to plug in my magic wand, so I have to do it manually. All right, so we're gonna get into a discussion of different types of reactions, and you've been exposed to that already, I think, with one of the labs. But we're gonna work on it again, and maybe go into some more detail, and then we'll get into some theories about what drives chemical reactions. And then we'll talk about a little bit of thermochemistry as heat and related to chemical reactions. And then we'll talk about chemical equilibrium and equilibrium constants, and then Le Chatelier's principle. I don't think we've done that one. No, that's the last lab. All right, so the discussion we have today on Le Chatelier's principle will be keep those thoughts in mind for the last lab. The one that we've got coming up next week is osmosis and dialysis. All right. So a chemical reaction is actually a process by which at least one substance is changed into a different substance. And by that I mean it has a completely different identity. It has different chemical properties, different physical properties than the reactant. You can get more than one reactant together and produce one product, or you can get more than one reactant and produce multiple products. So the sky is really the limit. Now we've classified chemical reactions based upon a generic understanding of what has come together on the reactant side and what goes out on the product side. But keep in mind that these classifications can overlap. So you can have, let's see, a good example would be, you could have an exchange reaction there on our list. It can also be an oxidation reduction reaction, or it could be a combustion. Right, so you can have several tags for the same reaction. And we'll go through these one by one. A combination reaction is one in which the simplest form of combination is one in which you have an element plus another element makes a compound with those two elements. The simplest example I can think of is sodium metal plus chlorine gas yields table salt. Right? And we need to balance it, of course. So that would be a combination reaction or a synthesis. It's often called a synthesis. The general idea is that simple makes complex. So there are times when the simplicity is not just an element, it could be a compound, but the result would be something more complex than either of the reactants or any of the reactants that go into the chemical reaction. I should start writing those up there, just in case the slides don't catch. Decomposition reaction. A decomposition is the inverse. It's like the synthesis reaction in reverse. So in this case, we would have XY yields an individual X and a Y. They have an example there. I like this one better. We have water, and you drive a direct current through it and split the hydrogen and oxygen apart. And you get hydrogen gas and oxygen gas. Well, let's see, we need to balance that, don't we? 2 here and 2 there. So that would be a decomposition. All right. A displacement reaction or a single replacement. Either one is proper. I like single replacement. I think it's more descriptive. So if you have a compound like a cation and anion together, and then you have an element, this element will replace one of those. In the example, well, let's see, they have X and Y, Z. Well, that's okay, this works. I'm going to replace that X with this Z. So we'd have ZY plus X. That's a single replacement. And the example they give is a good one, where we have iron reacting with, I got a better one. Where we have aluminum reacting with iron 3 oxide. And it produces pure iron plus aluminum oxide. Okay? Those are all solids. This reaction is thermite. Have you ever seen a video of a thermite reaction? It's extremely energetic, very high energy. In fact, the railroads still use this reaction to weld rails together. They put this concoction around the rail joint, and then they cover it with some refractory material like maybe sand. And then they put a big dome over it, and they have an igniter in there. It takes a lot of energy to get it started, but once it goes, it is hell on earth. And it produces liquid iron in that joint, and the weld is stronger than the rail. Then all they have to do now is go in and grind it smooth. That's thermite, and it's a single replacement reaction. All right. And by the way, that reaction, as well as the one that they show you in the slide, is also an oxidation reduction reaction. I'll explain oxidation reduction in a minute. Just to keep that in mind. This is one of those cases where a single replacement is also another type of reaction. A double replacement, or they call it an exchange. Again, I like double replacement better. It's more descriptive. And I'm going to use their example here rather than just write out A, B, C, and X, Y, Z. So we have silver nitrate in aqueous solution. and then we combine that with sodium chloride in aqueous solution. And it forms a solid, right? I think, have we done that in this, or was it my other class? Where we made, I remember, it was, let's see, I was looking for the right lab. Signs of chemical change. I think it was one of those reactions where we had silver chloride and we made a precipitate. It's like a white cloudy something. I think we did that one. Anyway, that, and then plus sodium nitrate in aqueous solution. This is a double replacement. Sodium changes places with silver, and that gives you sodium nitrate and silver chloride. Double replacement. Now, typically, these types of reactions require the formation of either, usually precipitate is 99 times out of 100 is what drives the reaction. If you form a precipitate from these two aqueous solutions, it's going to drive the reaction toward products. All right. Combustion reaction. I'll use something a little simpler. We'll use methane plus oxygen gas yields carbon dioxide plus water. And this is a gas. And I think at standard temperature and pressure, that's a liquid. So, in order to have a combustion reaction, one of the reactants must be oxygen. Let's see. There we go. That's balanced. This is also an oxidation reaction. This is a combustion. Anytime you have oxygen reacting with something to produce products, it's a combustion. I need a fresh marker. There we go. Okay, I guess we're gonna, hold on a second, let me get my hard copy out so I can sort of look ahead. Because I don't want to steal my own thunder. Okay, yeah, we're going to talk about oxidation reduction in a minute, but of the reactions we've discussed so far, the synthesis, decomposition, single replacement, double replacement, let's see if we can identify which this one is. And I'll write it on the board just in case the slides don't show. So this is 4HNO3 yields 4NO2 plus 2H2O plus O2. Okay, what we've got here is a compound breaking down into simpler substances. That would be a decomposition reaction. This is not the kind where you get elements formed from the compound, which is implied in that XY scenario, or XY yields X plus Y. That implies elemental decomposition, but this is this one makes several simpler forms, and that's a decomposition. Classify each one of these. All right. Forgot that board's not magnetized. Magnesium plus 2 hydrogen chloride. So this is A. Magnesium metal plus 2
HCl,
This is an aqueous, yes.
yields magnesium chloride
Aqueous.
plus hydrogen gas. Okay.
All right, what type of reaction is that? Oh, I've got the answer there. Okay, that's the problem with, I couldn't get my PowerPoint slides to work. So I had to go to the PDF. And the PDF has everything on the slide right there at once. So we get the answers at the same time. So this is a displacement, or I like a single replacement reaction. This magnesium replaces that hydrogen. So we get magnesium and chlorine together in this compound, plus the hydrogen is released as gas. This is a single replacement. How about B? HCl, gas plus ammonia, gas yields what? Ammonium chloride, which is a solid. All right, we've got simple making complex. This is a combination reaction or a synthesis. And then the last one, 4 ammonias. They don't say what the form is. That's okay. Plus 5 oxygens yields 4 nitrogen monoxide plus 6 water. All right? So the clue here is oxygen. This is a combustion reaction. Okay? All right. All right, now for oxidation reduction reactions, or redox for short. We don't say ox-red, it just doesn't sound right. So we say redox. A redox reaction is one in which electrons must be transferred during the reaction. We'll go back to my original example where we have sodium metal plus chlorine gas yields sodium chloride, solid. These are both neutral, right? They have balanced electron-proton in their makeup. Over here, we know that this sodium is a +1 charge and that chlorine is a -1 charge. Let's see, need 2 there and 2 there. Okay, so how did they get to be these ions from these neutral atoms? They had to exchange electrons. So this metals like to lose electrons. They just love it. Nonmetals like to gain electrons. So an electron is transferred here from sodium to chlorine. And when you lose an electron, you have an excess of protons, in this case 1, so you have a plus charge, and chlorine gets 1 extra electron, which makes it a net negative. That's an oxidation reduction reaction. And then, of course, non-redox, and there are a great many of those types of reactions. There's no transfer of electrons. Okay, here's a clue. In order to, sometimes this clue works. If you have a reaction in which there is an element on one side of the arrow, let's say it's over here, and you have, so this would be a single replacement. If there's an element on this side, and that element is in a compound on the other side,
So let's say it's xz plus y.
then there has to be a transfer of electrons. So this single replacement is also a redox, because all elements have zero charge. And when they're in a compound, they're either charged or they have a slight charge. If it's a covalent compound, then there will be some imbalance. But electrons must be transferred in order for this to happen. Okay, so if you can't use that clue, sometimes you need to have a set of rules to tell you whether or not an electron has been lost or gained by any particular element in the reaction. And for that, we use what's called oxidation states or oxidation numbers. Now, this is not to say that the oxidation number, whether it's +1, +2, +3, or -1, -2, -3, whatever, the oxidation number doesn't necessarily mean that there's a charge involved. It's a bookkeeping scheme for electrons. So, let's go through the rules. If the element stands alone, like this one, its oxidation number is 0. All elements in their most stable form at room temperature and 1 atmosphere pressure are always oxidation number 0. Okay? If there's an ion, right, that's a plus, this is a minus, its oxidation is the charge. So in that case, our bookkeeping scheme addresses the oxidation number as exactly the same charge. Now there are others that we assume. The oxidation numbers for group 1 are the alkali metals in compounds will be +1. So potassium in a compound like this, it'll be a +1. Lithium or rubidium, they're always +1 if they're in compounds. Okay? Alkaline earths, their next door neighbors, like magnesium, calcium, strontium, if these are in compounds, they're always a 2+ charge and a 2+ oxidation state. Okay? Oxidation number for hydrogen most often is +1. If the hydrogen is located, say, in a compound like water, hydrogen comes first, it's a +1. However, if hydrogen is combined with a metal, and it may not be in this list, if hydrogen is combined with a metal like sodium, it's a -1. Because the sodium is an alkali metal, it has to be a +1. That's sodium hydride would make hydrogen a -1. But most of the time, and particularly when hydrogen comes first in the compound, it's a +1. Oxidation number for oxygen is -2. And, well, the other members of the group, sulfur, selenium, tellurium, they vary. Right, so we can't assign them an absolute value. But oxygen is given a -2 unless it's a peroxide. So what's a peroxide? Well, it's where 2 oxygens are bound together like that. And then we have that attached to something, and this is attached to something. That's a peroxide. So both of those oxygens together have a 2- oxidation,
And each one then must have a 1 minus.
Okay, that's the one exception to the oxygen rule. Okay. In binary compounds, the more electronegative element is assigned a negative oxidation number equal to its charge in the binary ionic compound. So let's see, what's an example? If we have calcium sulfide,
Calcium is an alkaline earth, so it has a 2+ charge. That means sulfur would have to be
a 2- charge. There's no other option. I think that's what that rule is getting at. 7, for compounds, the sum of the oxidation numbers is always equal to 0. For neutral compounds, so water would be, the sum would be 0. Sodium chloride, the sum would be 0. Let's see, even for covalent compounds like sulfur dioxide, the sum would be 0. If, however, you have a polyatomic ion,
like, say, nitrate,
it has a 1- charge,
the sum of these oxidation states must be -1. So if oxygen is going to be a -2, then we have 3 times
a -2 is a -6.
And the way I do it is I hold one of those negatives out for this one.
So we only have to balance a -5 with the nitrogen.
That means the nitrogen has to be a +5.
And that way, and you go back and check yourself,
You've got 3 times 2 minus is 6 minus, and +4
is 1 minus.
So we've got our...
I find myself making fewer mistakes when I do it that way. Okay, let's do a couple of these. Let's see, potassium dichromate.
We have K2Cr2O7.
That's a neutral compound. Potassium is an alkali metal,
so it has to be a +1. Oxygen is a -2. So 7 times a -2 is -14, and 2 times a plus is +2. This would be a -12, right?
So
that means chromium, these 2 chromiums must be a +12. So each one of them has to be
only 6+.
Okay, if you add them together, you find out that
that's equal to 0. Let's see, let's do another one. How about PCl5?
Right.
Halogens typically are -1.
If you're confronted with a halogen attached to some other
non-metal, go for the halogen first and set it at -1.
Then that makes a -5
for the chlorine.
That means this one phosphorus must be
5+. Now chlorine can assume different oxidation numbers. Fluorine doesn't, and I don't remember seeing fluorine in that list.
But fluorine, we always give fluorine a -1.
Nothing else.
But if we have, say, chlorine and fluorine together,
I don't know, I can't think of a good example.
But if you had fluorine and, say, 3 of those and chlorine, then we would go to the fluorine first.
Let me check something first.
Let me look at the periodic table. Is that a valid
Yeah. You'll notice in this periodic table and in the ones that always attached to your review documents, in the upper right-hand corner, there are several numbers, minuses and plus numbers. Those are oxidation numbers. And they reference what we're doing here. And that would be a good place to check and confirm that chlorine can have a +3. So if this is a -1, that means 3 minuses, 3 pluses. This has to be a 3+. So we go with a more electronegative first, and that says that fluorine is a -1, and then we calculate the chlorine. Keeping in mind that this is still a bookkeeping scheme, right? We can't claim that there's a charge on chlorine. In fact, they're both nonmetals, so the bond is probably covalent anyway. They're sharing electrons. But it's a way to keep track of electron movement in redox reactions. Okay, so determine whether a reaction is either redox or non-redox. You calculate the oxidation numbers for the elements, and you look at the element on one side of the reaction versus the other side and see if its oxidation state has changed. If its oxidation state has changed, then yeah, you have transferred electrons. Calcium and chlorine together, that's a pretty violent reaction. And this just illustrates that the oxidation number changed from 0 for each one of the elements to a +2 for calcium and a -1 for chlorine. I hope they're doing that under a hood. Okay, oxidation numbers. What's the oxidation number for sulfur in H2SO4? Remember that one? If this is in aqueous solution, what do we call it? Right? There's oxygen there, so we don't say hydro. And it's in aqueous, so it's an acid. Right? So this part of the molecule is a polyatomic ion called sulfate. So H's become X. This is sulfuric acid. Okay, now we're going to calculate the oxidation state for sulfur. Hydrogen's first, so it has a 1+ oxidation number. So that means 2 pluses here. Oxygen is 2-, so it has 8 minuses here. Right? Put those together, we get a -6. That means this sulfur has to be a +6 to balance it. Okay. Now, when we set up a reaction, when we want to write a chemical reaction, we have names for the reactants and the products, depending on what happens to them during the reaction. If this is a redox reaction, then we say that the species that loses electrons is oxidized, and the species that gains those electrons is reduced. And these two always occur together. Oxidation, reduction, you never have them separate. You can't have one without the other. So there's the mnemonic for remembering what that means, how to tell the difference. Oil rig. So oxidation is loss of electrons, and reduction is gain. And so we're going to have an example in a second. Also, the species that is oxidized is the reducing agent. In other words, since it's oxidized, it loses electrons to something. And that means it is the agent by which the other one is reduced. So anything that's oxidized serves as the reducing agent. It produces the electrons that go to the other species and reduce it. Let's see. All right, I'm not too sure about this chart. It says that but I put it in here because it's in your book, and if you read it, I don't want you to be confused. When a species is oxidized, its oxidation number increases. So if it's negative, it just gets smaller negative. Or it might get smaller negative until it gets to 0, and then it can start going positive. Right? If we say, oh, here's a perfect example. Our earlier example of methane plus oxygen, this combustion reaction, produces carbon dioxide and water. So the oxidation numbers here, that one's 0. The oxygens are 2 minus, this is 1 plus, this is 2 minus. That means with a 4 minus here, this one has to be a 4 plus. But over here, this one is plus 4. This one is minus 4. Right. So oxygen has gone from 0 to 2 minus in 2 different locations, actually. So what happened to the oxygen? It gained electrons. It was reduced. And it serves as the oxidizing agent for carbon. So this carbon goes from a minus 4 to a plus 4. So how many electrons had to transfer in order to get there? Well, to go from minus 4 to 0, it had to lose 4 electrons. But then from 0 to plus 4, it had to lose 4 more. So there was a loss of 8 electrons for each carbon. And that's not balanced yet, is it? No. 2 there, 2 here. That's balanced. Okay, so, and the other thing that you need to know and remember, with grab onto it with all 4 feet, is that the number of electrons transferred during oxidation must be equal to the number of electrons transferred for reduction. So these 8 electrons have to go somewhere, right? They go to this oxygen. And they go to this oxygen. They go 2 places. So this one has gain. How many electrons to go from here to here and here to here? It had to gain 2 electrons. 2 electrons per oxygen. All right? So how many oxygens do we have? Well, we have 2 here and we have 2 here. So times 4 equals 8 electrons transferred. So the electrons balance. And I like to use these arrows to direct me so I don't get confused on where things are going. If you just draw the numbers up there, sometimes you can get lost in the confusion. Back to the slide. The reduction is a decrease in oxidation number. So if it starts off positive, it could be less positive, or it could be more negative eventually. And there are other examples for that. In this case, oxygen went from 0 to 2 minus. So it went more negative from neutrality. Okay. So let's go to the next one. So in this reaction, what is oxidized and what acts as the reducing agent? So let's see, copper plus silver nitrate yields, and this is a single replacement reaction. Copper replaces silver. So we have silver here plus copper nitrate. And let's see, we've got 2 of these, 2 of these, and this one is 2 here. So we want to find out which one was oxidized. That is, which one, OIL, lost electrons.
So oxygen is 0, silver is 0 here. This nitrate is a -1, so that means silver has to be a +1. And notice that this nitrate stays intact on both sides of the equation. So in order to do our balancing act, we don't need to break this apart to answer the question. Okay, so that means if this is -1 here, we got two minuses, that means this copper has to be a +2. Okay, so we're looking for the one that lost electrons. Copper went from 0 to 2+. So it lost 2 electrons for each copper. Right? And 2 electrons total, actually. And what was the reducing agent? Let's see. What's oxidized and what acts as, well, copper's both. It's oxidized, which means it is the reducing agent. Silver was reduced. It went from +1 to 0, and it's the oxidizing agent. Okay. Which of the following are oxidation reduction reactions? All right. Identify the oxidizing agent and the reducing agent. All right. A, we have zinc 2HCl. Zinc plus 2HCl yields ZnCl2, yep, plus H2 gas. Okay, is this an oxidation reduction reaction? We can use the trick for this one, right? There's an element here, and it shows up in a compound there. So this is definitely an oxidation reduction reaction. We just need to find out the oxidizing agent and the reducing agent. So that's 0. That's a 0. This is a +1. This is a -1. This is a -1, so that makes this one a +2. So when we go from zinc to zinc ion, we had to lose 2 electrons per zinc. And when we go from this hydrogen, see, chlorine didn't change, but hydrogen did. When we go from +1 to 0, we had to gain 1 electron per hydrogen, times 2 equals 2 electrons. So that means 2 electrons balance. Okay, which one's the oxidizing agent? The oxidizing agent is the one that's reduced, the one that gained electrons. This is the oxidizing agent. This is the reducing agent. All right. Let's see. How about B? Is this? B is what I would call an incomplete reaction. It's left out the spectators. Notice the charges don't balance. So, well, actually, in this case, they do balance. But we don't have the counter cations that go with them for the hydroxyls or for the dichromates or for the chromates on the other side. And they're not necessary. Let's see, Cr2O7 2 minus, Cr2O7 2 minus, plus what? 2OH minus yields CrO4 2 minus, 2 of those, and H2O. Okay? So oxidation states here. Well, in this case, hydrogen may come second, but it's still 2 minus, this is +1. This is a +1, this is a 2 minus. So the oxygen and the hydrogen didn't do anything. And the oxygen here is 2 minus. But it has 14, hold 2 out, minus 12. So with 2 of these, we need plus 12. That means this is plus 6. How about this one? Right? This one's a minus 2 times 8 is minus 8. Hold 2 out, minus 6 if we need to balance, plus 6. Chromium didn't change either. Oxygen, chromium, hydrogen, none of them changed. This is a non-redox reaction. So that's where you stop. If you don't have a redox, you can't have an oxidizing agent or a reducing agent. Okay, last. Actually, I like this one the best, and I'll tell you why in just a second. Copper 1 chloride yields copper 2 chloride plus copper metal. Okay, so this one's a 0, and this tells us it's a redox because there's a metal here. This is an element coming from a compound. Okay, this is a minus 1, so this has to be a plus 2. This is a minus 1, this is a plus 1. So notice copper went 2 different directions. Right? In one case, it went to here. And one of these coppers, see there are two here? One of these provided a copper that was oxidized. Loss 1 electron per copper. And the other copper went to here. And this one gained 1 electron per copper. Okay? This is called, I'll write it down here. This is called a disproportionation reaction. Disproportionation reaction, where, well, this is the simplest explanation. This copper went 2 different directions. It was not proportional. It didn't go just one direction. It went, one of them went this way, the other one went this way. But that is a redox, and loss of electrons means it was oxidized, so this is the reducing agent. And it's also the oxidizing agent. Okay. Now let's take a look at a theory. The theory behind chemical reactions. I usually introduce this theory in my general chemistry class for a discussion of kinetics, speed of reaction. But this collision theory is just what it says. During a chemical reaction, the reactants must collide with one another. They have to impact one another at some point. As individual atoms and molecules, they have to meet. Okay? And so there has to be a collision. Let's see. Collision theory. I have to remember that that may not come through. So I'll write it up here. So there has to be a collision of molecules or atoms. Molecules and atoms. And when they do that, there has to be sufficient energy. We call it activation energy. So, on an individual collision basis, if there's not enough energy, then the reactants bounce off each other and nothing happens. There has to be enough energy in order to do what? You have to break bonds before you can form them. So they go through a state called an activated complex. You have to have enough energy to form the activated complex.
then you can produce products. But that's not the only condition. If the bonds that are to be broken and later formed are not on the same sides of the molecule that are colliding, then nothing happens there, even if they have enough energy. So you need orientation has to be correct. So they have to collide. If they collide this way with enough energy, but the reaction sites are on the opposite sides, nothing happens. Now, of course, there are types of reactions where there's only one reactant. So what happens there? Right? Do you still need a collision? Well, sometimes you do need a collision. Like that last reactant, copper chloride, copper 2 chloride. When it copper 1 chloride, when it reacted, it had to bounce off one of its neighbors in order to disproportionately oxidize and reduce the copper from either side. But sometimes you have a compound that just simply decomposes, right? So the energy that you need for that one could be realized in a collision, but it doesn't react with the other object. It just absorbs enough energy to break bonds. Or it could be energy of vibration. You know, the molecules, the bonds will stretch, or the bonds will flex this way and that way. Sometimes that's all you need, enough energy to make those bonds break, and then you form products. So this is a generalized idea. There we go. Okay, we got several slides that just go into the details that I put up here. Reactant molecules, ions, or atoms must come in contact. They have to collide. If there's two or more of them, they must collide in order for a reaction to occur. There's a minimum amount of kinetic energy that's required for the collision, and they have to be oriented properly. And here's an interesting note. If you have two reactants that have to collide in order to cause the reaction to proceed, that gives you one reaction rate. But if there must be three reactants collide in order to give you a reaction rate, that is necessarily going to be a slower rate, because the probability of getting three together with enough energy and oriented properly is much less than it is for just two. All right, so here's an example where nitrogen dioxide and carbon monoxide, if they have enough energy and they're oriented properly, and I'm not going to draw that picture on the board, so our viewing audience might miss out on this one if they're not looking at their hard copies. And then the other examples below, the orientation is not proper, so there's no reaction that occurs. Okay, these are the three factors necessary: collision, activation energy, proper orientation. And what they mean by low activation energy is the reaction itself has a low activation energy, so they don't have to have as much energy when they come together in order to make the reaction occur. If the activation energy is very high, then the probability that they're going to have enough energy for any individual collision is going to be low, and the reaction is going to proceed slower. I think we've got diagrams coming up where it will explain that. Now let's talk a little bit about thermochemistry. An exothermic reaction is one that gets hot. In other words, it produces energy from the reaction. And it's useful to think of a reaction in terms of system
and surroundings. Okay? And everything is referenced in terms of the system. So if the system gives off heat, and we use a little Q for heat here, if it gives off heat, it's losing, the system is losing heat. So the sign on that value, whatever it is, so many kilojoules per mole, is going to be negative. If the reaction absorbs heat from its surroundings, then it's going to be positive because everything is referenced to the system. Now, if we do that in terms of, let's go back to our methane again, producing carbon dioxide and water. Let's see, we need 2 here and 2 there. We know that when we burn methane, right? If you got a gas stove at home, now assuming you're not using propane, if you're using natural gas from a trunk line, then it's going to be methane. So methane and oxygen is going to produce carbon dioxide and water and give off heat. So we know it's exothermic. Exo means out of. Well, it's useful to think of this reaction in terms of conservation of energy, right? The total amount of energy in all of these bonds over here is a certain amount, and the total amount of energy over here is a certain amount. So if this side has less energy, the energy of the products and energy of the reactants, if this side is less than that side, then where did the energy go? Well, it's given off as heat, or sometimes light, or other forms. But sometimes it's informative to say, all right, let's account for the heat as a reactant or product. So if it gives off heat, that means with energy higher over here than it is over here, then we need to add in the amount of heat that's produced. And for an exothermic reaction, that delta H is called enthalpy. The heat shows up as a product. Whereas if it's an endothermic reaction, then the heat would show up over here and be added into whatever the products are. I think that's the next slide. Oh, no, we get a diagram. Okay. Let's see. Let's draw it over here. So this is reaction progress. Okay. And this is energy. Total energy of whatever species are involved. So here, if we start off with a large amount of energy here for our reactants, and we need some energy as the reaction progresses. Think of this in terms of a collision. As the reactants come together, we need to add some energy to them. Okay? And up here is the activated complex. And then if we get enough energy up here, this is activation energy. Then we can go over the hump and go down to products here. So at this level we'll have products. And the total energy here is less for the products than it is for the reactants. And this over here is the amount of energy that's produced in an exothermic reaction. Okay. All right. Endothermic reactions are like exothermic reactions flipped around the other direction. So if we turn this arrow around and said these are the reactants and those are the products,
then we would be claiming an endothermic process because we would have to add heat in here in order to get, have to add energy in here in order to get these as products. A very important endothermic reaction is photosynthesis. The energy that enters the reaction cycle comes from the sun. Next door? Okay. And if we draw for an endothermic, this is exothermic. If we draw a similar diagram for endothermic, let's see, I'll write endothermic in a minute. We actually start off with lower energy for the reactants, and we need a lot more activation energy because the products are going to be at a higher energy level. Products. So the activation energy for an endothermic is usually higher. And if we flip this one around, the activation energy would be from here to here. So it'd be a lot bigger to go the reverse direction. This is endothermic. All right, and there's a slide with the same thing on it. And the amount of energy here, this is delta H. This delta H is going to be a negative value because relative to the system is losing energy. But here, the delta H is positive because we've added this much energy into the products from here to here. Okay, which of these is correct? During an exothermic reaction, the average energy of the products is higher than the average energy of the reactants. It's the other way around. Well, that's why C is the answer. The average energy of the products is lower than the average energy of the reactants. That's an exothermic reaction. B, an endothermic reaction, the average energy of the products is lower than the average energy of the reactants. No, it's the other way around. Right, you can tell from the diagram which one is lower than the other. Now that we've got these diagrams on here, we can talk about reaction rates. How fast does the reaction proceed? And we call this, let's see, I'm going to have to make some room here. The study of reaction rates is kinetics. How fast does the reaction proceed? And it's usually studied in terms of initial reaction. In other words, we start off with a certain amount of reaction and the reactants disappear. It's easier to follow them that way than it is to try to track the products that are produced. Now you can do it both ways, but it's easier to do it from the reactant side than from the product side. So what factors affect the reaction rates? Well, the physical nature of the reactants, in other words, their phases, solid, liquid, or gas, will have a bearing on the reaction rate. Remember the collision theory. In order for a reaction to occur, the reactants must collide. So if you have this big chunk here of, say, calcium, and you have this big chunk over here of sulfur, then where are they going to collide? Well, when you bring them together, they can only collide at their interfaces where they touch. Right? So that reaction is going to be really slow. But what if you say calcium is pulverized?
calcium dust and sulfur dust.
Mix them together, and then give them enough activation energy to get them started. Then that reaction is going to go really fast.
Similarly, let's see.
Reaction temperature. Right. Okay. So particle size, physical nature, includes particle size.
I need to make some more room. So phase makes a difference. And for solids, that's particle size. Will increase the rate.
Liquids, however, tend to be more, they have to be miscible.
Miscibility.
In other words, if they're separated, like oil and water, they're only going to react where they interface. But if they're miscible, then you get all the reactants mixed in the same space, and there's more chance for them to interact with one another. For gases will give you the fastest rate, typically,
because they are they form solutions.
Right? They're infinitely miscible. So you've got the gases mixed together, always homogeneous mixture.
All right, second thing
That will determine the reaction rate is concentrations. If we go back to the collision model, the higher the concentration, the higher the probability of collisions occurring, because you got more reactants in there in closer proximity. So the reactant concentration has a bearing on the velocity and the speed of the reaction. Reaction temperature. Reaction temperature has an influence based on the collision model because that supplies the activation energy.
Remember, temperature is a measure of the average kinetic energy
Of all the molecules in a substance. So if you increase the temperature, you increase their kinetic energy. When they collide, they have more energy. So the collision model tells you that you're more likely to meet the activation energy threshold for the reaction to occur.
And last but not least, catalysts. So what does a catalyst do?
Well, in short, a catalyst speeds up a reaction, causes a reaction to occur faster. But the reason it does that
Is catalysts provide alternate mechanism
for the reaction. They give it a different pathway. So when you look at the energy diagram for a catalyzed reaction, you find that the activation energy is much lower. Now, a catalyst enters into the reaction, but it's not used up by the reaction. In other words, it goes in one end and it comes out the other. So if you write your reaction and put a catalyst in there, you usually don't put it on reactants or product size. You put it on the arrow because it has an effect on the reaction rate, but is not consumed by the reaction. A good example of that is the catalytic converter in your car. It takes incomplete combustion products from your engine, runs them over platinum palladium catalyst, which is in a ceramic matrix, and it causes those reactants to further proceed to less harmful products. you get oxides of nitrogen and incomplete carbon combustion products, and the catalytic converter speeds up the reaction whereby you can move those incomplete combustion products to nitrogen gas, carbon dioxide, and water. Now, you don't get any benefit from it. I mean, you just get a hot catalytic converter. But at least you don't pollute. So those four factors have a direct bearing on the reaction rates, how fast the reaction goes. Oh, I forgot I had slides on this one. Okay, let's see if I got it right. Physical state, the physical nature of the reactants, the physical state, solid, liquid, or gas, and particle size. Okay, got that one. When the reactants are all in the same physical state, the reaction rate is generally faster. Liquid states faster than between solid state reactants. And the fastest is between gaseous states. Okay, so those are all true statements that I gave you before. Particle size just means that there's you get more intimate contact of reactants. And a good example there is coal mine dust explosions. Right? As long as the coal is in the wall or in big chunks, then the risk is low for reactions with oxygen. But during the mining process, you produce coal dust. And that coal does several things. It goes into the miner's lungs, right, and gives them black lung. But it can also mix with the air that's being blown through the mine to supply the miners with oxygen. But it also supplies the coal dust with oxygen, and carbon, oxygen combined make carbon dioxide, and they give off, it's very exothermic. So all they need is a little activation energy. They need the right amount of oxygen with the coal dust amount. Right? You have threshold amounts there, percentage amounts. And then all you need is activation energy. Any spark will set it off. Coal mine gas explosions too occur, right? If you had a gas pocket. And methane is odorless. You can't smell it. The only reason we can smell natural gas coming out of the pipes in our home is because they dope it with ethyl mercaptan, which is a sulfur-containing compound, and it stinks really bad in very small concentrations. So when it first comes out of the pipe, if you got a leak, you can smell it. But if you go away on vacation, or you lock up your home for the summer, and you go back north for a while, and then you go back south, you've had a gas leak all that time, the gas will still be there, but the sulfur will have dissipated. You can't smell it. So all you have to do is flip a light switch, and boom. That's what happened to one of our doctors, Dr. Karam. I don't know if you heard about that. He's a cardiologist in Beckley. He and his wife have a home down in North Carolina, and they had been to Ohio, I think, to visit grandkids. And they went to their home in North Carolina, opened it up, and they went their separate ways to start getting things back in order. His wife was upstairs, and he was in the basement, and she flipped the light switch, and boom, it killed her and buried him in the house. They recovered him. He's okay now. But they couldn't smell it because the leak had been there for so long that the sulfur had dissipated. And you can't smell methane. Right? So all you need, so here's the lesson. If you're rich enough to have a second house and it uses gas, then the first thing you do when you walk into your house is open all the windows. Even if it's in the dead of winter, do it. And then, if you suspect a gas leak, have somebody come in with a sniffer that can detect methane. Okay, concentrations. That has a bearing also on reaction rates. And an increase in concentration causes an increase in reaction rates. Now, this is relative. Some reactions occur very slowly, but if you increase the concentration of the reactants, you will increase the rate. It may still be slow, but it'll be faster than it was before. Okay. Temperature supplies the activation energy. We got that right. Catalysts. Catalysts increase the reaction rate by providing an alternate reaction pathway. That's what I meant here. And that alternate pathway has a lower activation energy required. So if you have hydrogen peroxide, for instance, let's put it over here. If you have hydrogen peroxide, right, it will, over time, it will spontaneously decompose into oxygen gas and water. Okay? But you can keep it in your medicine cabinet for a long time. That 3% solution will be active for quite a long time. And they put stabilizers in it too to keep it from reacting. But if you want to react faster, generally you want something that's 30% or greater. Not 3% from your medicine cabinet. You won't see the reaction very fast. Add iodide, iodide ions, as a catalyst, right? And this will decompose very fast. I had a student here at Southern. It's been several years now, 3 or 4 years ago. He and his, I think she was his girlfriend at the time. I don't know if they were married. But he was expecting a child, and they had a ultrasound tell him what the gender was. So they wanted a gender reveal party. Well, he was a science nerd, so he bought some 30% peroxide, and he put it in I guess it was a 2-liter bottle, and he had a solution of potassium iodide there. And you just dump it in, and it goes, just instant reaction. Well, to make it look better, you put a little bit of soap in it. It makes the bubbles. And then you put a color in it, right? If it's going to be a girl, you put red food color. If it's going to be a boy, you put blue food color. And they had a gender reveal. Only, and he showed me videos. They did it once, and they found out with the second ultrasound that that was wrong gender. So they did it again for the other gender.
That's crazy that they get it wrong. Now they do blood tests instead.
Ah, okay.
Yeah, my sister, they done a blood test for her gender of her baby.
So, do they get blood from the fetus?
No, the mom.
The mom? Oh,
Yeah.
I wonder how that works.
I have no idea. That's just how they done hers because she found out the gender at like real early, like 12 weeks I think.
Oh, I'm going to look into that, see how they do that. Are they looking for a specific hormone or?
I think so.
Yeah. Okay, so that's what a catalyst does. It speeds things up. And in fact, our bodies would not function without catalysts. We call them enzymes. We have enzymes in every cell that do two things, actually. Enzymes are catalysts, yes, but they're biological catalysts, and they do something else. They do catalyze reactions. They cause reactions to occur that normally wouldn't occur very fast. But enzymes are very, very specific for the reactions they catalyze. So there's a control factor there. They can be turned on and off. And generally speaking, not always, but generally speaking, an enzyme will only catalyze a reaction in one direction. So once it gets to this side, it can't go back. There are some exceptions that are troublesome. One enzyme called Rubisco, it's short for a very long name, is one of those that gives trouble with photosynthetic pathways because it will go both directions. But generally what you have is, if you want the reaction to go backwards, you need a second enzyme to catalyze the reverse reaction. Okay, so that's what you see with a catalyzed reaction is the activation energy is lowered, and that speeds up the reaction. Because there are more molecules with sufficient energy to react. If you lower the threshold, then the more molecules you will have at that same temperature will have sufficient energy to react, and you'll get a faster reaction. What's the function of a catalyst in a chemical reaction? Increase the rate by decreasing the activation energy. Pure and simple. Now, that was kinetics. That talks about reaction rates. Now we're going to talk about equilibrium. And in my general chemistry class, I always introduce the kinetics first. I think we can erase this now. Because an understanding of reaction rates helps with understanding equilibrium. And I'll explain that in just a second. So, while kinetics talks about what happens in between reactants and products, right, the activation part, equilibrium is only concerned with reactant concentrations and product concentrations. And for those reactions, we generally write an arrow in the middle like this, because the reaction can go forwards and backwards and forwards. And we're looking for a balance point, because most reactions will have some reactants left over and some products produced, and then they can go backwards and forwards. And the point at which we see that there's no change is when we call it equilibrium. So the concentrations, and that's the factor. We're talking about concentrations of, not absolute amounts, concentrations of reactants and concentrations of products stabilize for a reaction. And the stabilizing point is different for every reaction. So it has to be empirically determined. What we find, let's use this particular reaction, H2 plus I2. H2 plus I2 yields 2HI. Okay? We're going to start off that slide shows that this is the reaction rate on this scale. So we have reactants up here, and we have products down here. And initially, the reaction rate is very high. But as we convert these to products, then the reaction rate for HI slows down because we have fewer and fewer and fewer molecules, and concentration has an effect. So it's less concentrated, we have a slower rate. So the rate starts off really high and then goes down low. Well, for this side, when you're going back the other direction, and this would be the forward direction, right? This would be the reverse direction, going back the other direction. So the reaction rate for this reaction going backwards is 0 to start with, because there's no hydrogen iodide over there. So once you start building it up, the reaction rate increases. There's a point at which these two reaction rates, we would call it, say, R1 and R2. The reaction rates are equal. At that point, you have equilibrium. See, the thing about it is, on a macroscopic scale, you see a concentration here of this one, and a concentration of this one, and you reach a point where they don't change. That you look at them and say, they're not changing. But actually, on the microscopic scale, the activity is furious. It's going this way and that way at a furious pace, but they're balanced. The rates are exactly the same. So once we study kinetics, then we can have a better understanding of equilibrium. And at that point, we have an equilibrium, and we have concentrations for each one of these, and we can put them into an expression. Let's see. Well, okay, one of the conditions is the reaction has to be reversible. There are some reactions that the return rate is so low that we call them irreversible. Okay. Yeah, okay, we're going to get to it in a minute. Hold that thought. We're going to use, there's a mathematical expression that involves the concentrations of reactants and products. We call it the law of mass action. But before we do that, let's talk about what happens in this reaction. H2O plus carbon monoxide yields H2 gas plus carbon dioxide gas. Okay? Say we're at equilibrium. We've got some reactants left and we've got some products. All right? What happens if we add more water? Well, now you've got more reactants here. Right? So the water can react with carbon monoxide to make some more of these. The reaction is going to shift this direction until we reestablish that balance. Okay? That's because we have more collisions over here than we did before. So the reaction rate forward is going to speed up until the reverse reaction balances it out. What if we add more hydrogen? Well, if we add more hydrogen, similar scenario. It's already at equilibrium now. We've got more collisions on this side, so the reaction rate's going to increase that direction until we reestablish the balance of reaction rates. So the reaction is going to shift this way for concentrations until we reach that balance point again. Now we can express, let's say we have a reaction where we have this reactant and that reactant, and this coefficient and that coefficient. And they're going to produce products with that coefficient and this product and this coefficient and this product. Okay? What we can do is at any given temperature, that's important, the temperature must be constant. At any given temperature, we can write an expression that will be equal to some constant. And the way we write it, this law of mass action, is we put the products in the numerator, the equilibrium concentration. That's what that bracket means. That square bracket means usually molarity. Square bracket means molarity at equilibrium. And we raise it to the coefficient power times the other product raised to its coefficient power. And then in the denominator, we put the concentration of the reactants to their coefficient powers. And that's an equilibrium constant. At any given temperature, this value will be constant no matter what these are. If the position shifts, if we add one of these ingredients and make it shift, then the concentrations will change at equilibrium. But when you stick them in this formula, they'll still be equal to that K. That K is a constant. Okay. Like I said, square brackets refer to molar concentrations at equilibrium. Products are always in the numerator, reactants are always in the denominator. And the coefficients are the powers. Okay? When we write these equations and this expression for equilibrium, it's important to know what the phase is. If the phases are gases or they're in some sort of solution, aqueous solution is most common for us, then those factors, those concentrations will go into the expression. But if you have any solids or any pure liquids, they are not part of the expression because their concentrations do not change. So I have to give you an example. The other thing is when we calculate this KEQ, the units of measure are omitted. Okay? Because with any number of products and reactants and their powers, the sky's the limit for the units of measure. So we just leave the units of measure off and we're meticulous about the expressions. If you look at any reference manual for standard K values for a reaction, they won't have units with them. What they will say is whether the units are derived from molarity or from partial pressures of gases. Because you can express these in terms of molarity here, or you can have a K using partial pressures. Say if those are gases, we could say the pressure of C to the C power, the partial pressure of D to the D power, and then partial pressure of A to the little a power, and partial pressure of B to the little b power. And that will be a different value if these are gases, and you can express gases in molarity. That's possible. Or if they're all gases, you can express a Kp, and since they're in different units of measure, usually atmospheres, then the KEQ and the Kp are not the same value. So reference manuals will tell you whether the K is derived from molarity or partial pressures. Okay. Let's see. Okay, for this slide, how does the temperature affect an equilibrium? So in the first example, we have an exothermic reaction. Reactants yield products plus an enthalpy. Reactants yield products plus a delta H. This is exothermic. Okay? So, what happens to the K value, right? And the K value only involves these two. It doesn't involve the heat term. But we know that the heat's there. So, if we have a KEQ here with products over reactants, what's going to happen if this is an exothermic reaction and we increase the temperature? Right? Before, we said the temperature didn't change, right? But the K can be calculated for different temperatures. So in this case, if we increase the temperature, what's going to happen? Well, if we add heat, we're going to shift the reaction back this direction, right? We're adding a product. So we shift the reaction back toward reactants. Now the reactants are higher and the products are lower. The KEQ would decrease.
for temperature increase.
Right? Okay?
If it's an endothermic reaction, that means we would have reactants, and delta H would be on this side with products. So the KEQ in this case, if we add heat to an endothermic, it's going to shift toward products, and the KEQ would increase for temperature increase.
Okay? Now, other things we can tell about the KEQ. If the KEQ is very large,
Then we know
that the reaction goes more completely toward products because the numerator would be large in order to make the KEQ large, and the denominator would be small. So a large KEQ means products are favored. A small KEQ means just the opposite. Reactants are favored. Okay? Your book might say greater than 1 or less than 1, but that's difficult to prove because you've got these powers in here. And when you have powers involved, you can't say that things are exactly equal to 1 or greater than 1 or less than 1. So I say when the KEQ is large, equilibrium is toward the products. If it's small, equilibrium is toward the reactants. Now, I alluded to this before. There's a difference between equilibrium constant and equilibrium position. An equilibrium position references the absolute concentrations of the reactants and products. So if we're at equilibrium and we have certain concentrations here of reactants and products, that is an equilibrium position. And if we add one of these products, we shift the reactant action to the left and we change the equilibrium position. Okay, so you can have multiple different equilibrium positions, but only one equilibrium constant for any given temperature. Okay, this is table 9.2 in your book. It just summarizes everything for you. Okay, so let's take this same reaction we had before. H2 plus I2 yields 2HI.
H2 plus I2 yields 2HI.
Now, we have to assume that these are valid concentrations. Right? Iodine is typically solid at room temperature, but for this reaction, we've turned it into a gas.
Okay. So if we're saying everything is a gas, then we can put these terms into an equilibrium expression without worrying about whether they're gas, solid, or liquid, and whether they should or should not be included in the expression. So what would be the KEQ for this expression? Well, the concentration of HI goes in the numerator to the second power. Then the concentration of H2 goes in the denominator times to the first power times I2 to the first power.
So that would be the equilibrium expression for that equation. Now, we've been using Le Chatelier's principle up to now. When you add or remove reactants or products from a reaction that's at equilibrium, something happens. Le Chatelier put that into a system that was, well, at the time, it wasn't really understood. So he gave it some traction.
We understand it now, of course. But what Le Chatelier said was,
when you have a reaction at equilibrium, anything you do to disturb that reaction will be met by a response from the reaction to reestablish equilibrium. So what kind of disturbances can you do?
Well, let's see. Le Chatelier.
And of course, he was a Frenchman. What type of disturbances can you do? Well, you can
Add or subtract reactants or products,
right? You can change their concentrations. That's what we're doing. And if you add product to one side, it'll shift to the other side. If you subtract products from one side, from their product side, it will shift toward the product side. Okay, what else can we do? We can change the temperature. You can change the temperature and shift the equilibrium. In this case, when you shift the equilibrium, you're actually changing the K value. Right? Concentration changes. This is the easiest one to understand, is the change in concentrations. Change in temperature requires that you know whether the reaction is endothermic or exothermic in order to apply the Le Chatelier's principle.
Then when you have a reaction, A plus B yields C plus D, then you know which side to put the delta H on. Does it go over there or does it go over here?
If you know which side to put it on, then you can make an intelligent guess as to which way the reaction will move when you change the temperature. And we showed examples before, right? If it's exothermic and you increase the temperature, you're going to shift to the left. If it's endothermic and you increase the temperature, it's going to shift to the right. Because in this case, we treat the enthalpy, or the heat, as a reactant or product. And that's the most efficient way to do it. How about 3? Okay. Well, here's an example of changing the temperature for an exothermic reaction. If you have this reaction in which cobalt chloride ion is blue and the hydrated cobalt ion, this is a complex ion, is pink, then when you cool it down, when you take the blue and put it in ice, you cool it down and shift the reaction to the right because you're removing energy from an exothermic reaction and it shifts to the right. And you can see it as a color change. How about pressure? Under what circumstances would pressure have an effect on the reaction? Well, think about this. If you have a reaction, and the example there is Haber-Bosch process. That's a good one. This is a gas. This is a gas. And there are 3 of these. And in equilibrium with ammonia is a gas. And then it's exothermic. Okay? So we know what would happen to this reaction if it's at equilibrium and we increase the temperature. We drive the reaction toward the reactants and we wouldn't get much ammonia. That was Haber's problem. But what if we change the pressure? How would you change the pressure? Well, if we add more reactants, that would increase the pressure, but that would also fall under this category, so that'd be an easy fix, an understanding. But if we change the pressure by, volume change, right, then we haven't changed the, we haven't added anything or subtracted anything, we've just changed the concentration by squeezing them into a smaller volume, or letting them expand into a larger volume would decrease their concentration. So how do we know which way it's going to go, though? Well, you count the number of moles of gas on either side. Right? This is 3 plus 1 is 4. That's 4 moles of gas on the reactant side. On the product side, you only have 2 moles. Right? So if we increase the pressure by decreasing the volume, right, that's Boyle's law, decrease the volume, then the system is going to react in a way to alleviate that pressure. And it does so by reducing the number of moles. You reduce the number of moles of, total moles of gas, and how do you do that? Well, in this case, you shift to the right, because the products have fewer moles of gas. So increase the pressure by decreasing the volume means that you're going to get more product. And that's exactly what Haber did. He increased the pressure in his reaction vessel to hundreds of atmospheres. But he also heated it up to provide enough activation energy for the reaction. The problem was, when you heat it up, you drive the reaction to the left. So he compensated with an iron catalyst, which made the reaction go faster. And then, not only that, under pressure it drove the reaction this way, under high temperature it drove it this way, but with a catalyst it made it go faster. So as product was being produced, he would bleed off part of the reaction mixture into a separate line, which was cooled. And the boiling point of ammonia is much higher than nitrogen or hydrogen. So all he had to do was cool it a little bit. The ammonia would drop out as a liquid. He could extract that and send these gases back through the system. So he was driving the reaction to the right by removing product. Okay, so when you increase the pressure by decreasing the volume, the reaction is going to respond by moving to the side with fewer moles of gas. Now, what if both sides have the same moles of gas? It won't change. No change at all. Also, if you increase the pressure by inserting an inert gas that does not react with any of the products or reactants, you also don't change the reaction, because you haven't effectively increased the collision frequency for either side. Okay, so that's Le Chatelier's principle. Now, what does a catalyst do? Right? Catalyst. A catalyst does nothing for the equilibrium. Zero. All it does is changes the rate. There's no change in equilibrium, because a chemical catalyst catalyzes the reaction forward and reverse. Right? So it may speed up the forward reaction, but it also speeds up the reverse reaction. Okay. So what factors affect equilibrium reaction for Le Chatelier? Concentration, temperature, and pressure if gases are involved, and there's an uneven number of moles for reactants and products. Oh, we're down to concept questions. That means we're near the end.
of Chapter 9.
And let's see, the next time we meet, we'll cover Chapter 10, and then the week after that, we'll do a review. And that'll be the last week of regular classes, won't it? And the following week will be finals week, and that's when we'll have Exam 4. All right. So let's look at concept 1. A breathalyzer. Have you ever had to breathe into a breathalyzer before? Me either. Test you for a blood alcohol. This is the reaction that occurs. So if you've got ethanol in your system, some of it will be volatilized through your lungs. That's why they use the breathalyzer. It comes out in your exhale. And the amount that's in your breath is correlated with the amount that's in your blood. They've done tests to make the correlation properly. So they measure a certain amount in your breath. That means you have to have a certain amount in your blood. Okay, so this is one way to measure the amount of ethanol. They react potassium dichromate with ethanol and sulfuric acid. And it produces a color change from reddish orange to green in the presence of ethanol. In other words, it goes from potassium dichromate to chromium sulfate. And I'm sure chromium sulfate is the colored agent. Now this is a redox reaction, which is undergoing reduction. Let's see, in this reaction, something is undergoing reduction to something else, while something is on oxidation to something else. Something is the oxidizing agent, something is a reducing agent. So we just need to write this equation and determine the oxidation states for all the elements, and then track where the electrons went. All right, so I'm going to need a lot of space. Maybe I can go right through here. Potassium dichromate. All right, plus 3 ethanol plus 8 H2SO4, and that produces 2 chromium sulfate, and let's see, plus, am I going to have enough room? Potassium sulfate, and then 3 CH203COOH. This is acetic acid. Right. In your textbook, it might be written this way: C2H2H3O2. Same thing. And then 11 waters. All right. So, let's do our oxidation states. Potassium is +1. Oxygen is -2. We did this one earlier. This one's +6. Oxygen's -2. Hydrogen's +1. This is +1 for those hydrogens, +1 there. These carbons, I believe those carbons are -4. I think. It's a little more difficult to determine the oxidation states for these guys because, for other reasons. Sulfate.
Sulfate doesn't change, so it's a -2 total, and this is a +1. This is a +1, this is a -1 for the sulfate. Water is +1 and -2, and sulfate is -2. This chromium, since this is a -2 and we have 3 of them, that's a -6, right? So a +6 here means that this has to be a +3. So the chromium did change. The chromium gained electrons. It went from +6 to +3. So gain 3 electrons per chromium. Okay? How about this carbon is still -4, but this carbon is different. Right? We have this carbon, here, here, here. And then we have an oxygen here and there, like that. So what we have to do here is say, we might have to use a process called formal charge, which is a little bit different. How many electrons does carbon start with in its valence shell? Right. 1, 2, 3, 4. That's 4 electrons. So it starts off with 4 electrons. How many does it have from here? Well, the bonding is 1 electron here, so it gets half of each bond. 1, 2, 3, 4. -4, that's 0. So this carbon went to 0. So this carbon is 0. And that means that one of these carbons, I'm going to say this carbon right here, that carbon went from -4 to 0, which is a loss of 4 electrons per carbon. So, in this reaction, which is undergoing reduction? Gain electrons. So, chromium, this whole species with chromium in it, is undergoing reduction. So, it's the oxidizing agent. Let's see, it's probably on the next slide. Yeah. In this reaction, chromium 6+ is undergoing reduction to Cr3+. While ethanol is undergoing oxidation to acetic acid. And C2Cr207 is the oxidizing agent, right, because it's reduced, and the reducing agent is this one, is ethanol. Okay? I think there's a second one coming up, so we'll make room for it. Oops. Didn't mean to do that. That locks out that region for putting the shine on. There we go. Okay, let's see if I have a... No, that's it. Just that one. So we're done.